So next we have Jerry Sanders. Jerry's well known by everyone. He is the NASA In Situ Resource Utilization Systems Capability Lead, and he's here to share that information with you. Thank you, Jerry.
Thank you for inviting me to talk to everybody today. Go to the next chart, please. So I'm going to talk about two things. What is ISRU and the challenges for developing and integrating them. Many of them are questions that have been raised and discussed already. And then a little bit of information as to the current ISRU development and demonstration plans. My charts are pretty dense and hopefully they'll be posted afterwards since I'm going to go through these pretty quickly. Next. So again, what are the challenges for ISRU? Next. To begin with, I think we're all pretty much aware of the Artemis program and its intent, returning astronauts to the moon, the first woman and first person of color. What's really important for ISRU though is a couple of items. One is obviously learning to live and work on the moon, but involving commercial and international partners to make this happen is extremely important. So the Space Policy Directive 1, the Artemis Accords that were just discussed all play into this. Next chart. So what is ISRU? We define it as, in general, prospect to product. It involves any hardware or operations that harness and utilize in situ resources to make products and services. ISRU involves multiple disciplines and elements. By definition, it doesn't exist on its own. It needs a customer for the products. So that interaction is very important. And for our lunar activities, we basically have three primary objectives. One is to sustain and grow the lunar surface exploration program. One is to reduce the risk and prepare for human exploration of Mars. But the third one, again, is how do we expand both terrestrial economics as well as into the cislunar sphere. Next. This chart just gives an understanding of when we talk about ISRU, we break it down into four major categories: the destination reconnaissance and resource assessment. How do you acquire the resources, acquisition, isolation, and preparation, processing those resources into mission commodities, and then also supporting making mission commodities for manufacturing and construction. There are also some cross-cutting aspects such as planetary simulants and test facilities that we are also supporting. And the flow chart basically is used to show how we flow from one functional area to another. This connectivity allows us to really understand the interactions and the influences of upstream and downstream functions, as well as who are we coordinating with. Next. ISRU needs to be considered as part of a larger architecture. We need communications to and from the Earth and the local. We need extensive power capabilities, transportation to and from the sites with navigation aids most likely, loading and offloading aspects, fuel and support services. We'll need maintenance and repair over time, whether it's crew or robotics. And when we deal with the crew, we'll have to deal with living quarters, roads, and construction aspects. All of this to help us coordinate our mining activities, which include the excavation, the processing, dealing with the tailings, as well as our product storage and distribution. Next. You're all very familiar with this. From an ISRU perspective, we break down lunar resources into two bins: the regolith and the volatiles that may exist in the permanently shadowed craters. There's been fantastic discussions about that already. But since we are looking at the South Poles, in particular as one of our important destinations, we're considering the Highland regolith as well as what might be in the permanently shadowed craters in our plans. Next. We have four major development and implementation challenges. The first being, what are the resources there? Do they exist? form, what uncertainties are associated with them, and Kevin and others have talked about that to some extent. We have technical challenges. Can we economically, feasibly excavate and process these resources, the energy, the life, the performance? How reliable does this hardware need to be? We have operational challenges, the extreme environments, the temperatures, especially in permanently shadowed craters. The fact that we're operating in a lower gravity affects our surface interactions and liquid solid interactions and such. We have to operate potentially for extremely long periods of time without crew. This might not necessarily be as important for the moon because of the short communication delays, but gets incredibly important when we start thinking about Mars. And then we're going to have to start up and shut down our systems repeatedly, most likely, especially at the beginning until we have huge amounts of power. And then we have integration challenges. Systems need to be designed around using ISRU commodities. And so we need to work this at an architectural level. Next. To dive a little bit more into the challenges ISRU is specifically interested in, obviously the severe environments, the brace of regolith, the extreme temperatures, as well as the temperature changes that occur if you drive in and out of permanently shadowed craters. And then operating in low gravity, as I mentioned, the granular flow is different, liquid sloshing. When you kick up dust, it settles differently. Um, your inertial aspects have to be taken into consideration and such. Next chart. We did a very significant assessment of ISRU at the international level through the International Space Exploration Coordination Group, or ISECG. A report was released. In that report, we looked at the strategic knowledge gaps that League last looked at in 2016, and we went through all of them with an aspect of how important it is to ISRU in 5 major areas. We looked at when you would try to buy down those risks and more information as to what knowledge we need. We looked at the 2 major themes, understanding the lunar resource potential as well as how to live and work. So I highly encourage you to look at that report in the SKG definitions that we went through. Next. From a current lunar ISRU development and demonstration plan, next. ISRU falls into the Space Technology and Mission Directorate within NASA. We do coordinate with the Science Mission Directorate and the Human Exploration Program, obviously, but ISRU primarily falls in STMD. Which has a framework for all of the work that they are funding. And the work needs to fall into 4 thrusts: go, land, live, and explore. And ISRU falls into the live thrust. Next. STMD also has a large number of different technology development programs that go from the extremely low technology readiness level, the NIAC type of activities, all the way to high technology readiness level demonstrations. And so we have tried to influence every one of these different technology bins to hit ISRU and fill the portfolio of technologies. So, for example, there is a luster call that has just been released, Lunar Surface Technology Research, aimed at universities, and one of the areas is mineral beneficiation and size sorting. Next chart.
Jerry, excuse me. We
Yes.
have several open mics online. Please mute yourself if you're not speaking.
Thank you. I was trying to ignore those. Within STMD, to further help focus specific areas of development, they've created the Lunar Surface Innovation Initiative. to discuss six areas in particular. You heard a little bit about lunar dust. Um, ISRU and surface construction and excavation are other areas that are jointly tied. And I believe yesterday there were some very good talks on the construction and manufacturing aspects. Next chart. So from an ISRU perspective, we have several steps that we are working on. The idea is to maximize ground development and then use flights, particularly CLIPS, to develop the critical information and eliminate risks for full-scale implementation and commercialization. So first step is know your customers and your gaps. And so we spent a lot of time on that. In particular, working with the Lunar Surface Innovation Consortium is ongoing. Begin the development of on the ground of hardware and systems to raise the technology readiness level. Again, engage industry, academia, and the public through all of those different aspects, including challenges and such. Use CLIPS missions, particularly to understand the resources, as was mentioned, also to obtain critical data that we might not have from Apollo. Demonstrate proof of concepts, and then critical pieces of hardware. The idea is to take this to an end-to-end, what we call pilot plant, where we demonstrate from the beginning to the end the process excavation, processing, and product generation. We hope to use those products in some kind of demonstration, and by doing so, buy down the risk of full-scale implementation. Next chart. So what are the consumables or commodities? Again, the primary ones are water that might exist in the poles. There's a lot of uncertainty still, as was mentioned, but it does provide 100% of the propulsion capability or propellant mass that we might need, and it strongly influences where and how you might perform long-term surface exploration. Oxygen from regolith is also extremely important. Over 40% of the mass of regolith is oxygen in different mineral forms. The technologies are potentially less risky than some of the water mining technologies. A little bit more is known about them. And when you look at propulsion systems, you still get 75 to 80% of the propellant mass by just making the oxygen. And we hope a lot of these technologies could be applicable to Mars as well. And then our third major commodity is the construction feedstock, whether it's just bulk regolith or refined. We're starting to look at metals and slag that might come out of oxygen extraction techniques, as well as chemical and biological processing to refine those products into plastics or other items of interest. Next. For the resource assessment, we kind of think about three phases, all happening simultaneously to some extent. There's been discussion about the remote assessments. LRO is providing significant data to this day. We're looking at trying to perform some initial exploratory assessments, such as Viper, to get an understanding, initial ground truths. But eventually, we're going to have to do very focused assessments of those resources at specific sites so we can start planning and mapping our mining operations. Next chart. So when you look at what is NASA doing, it's doing a tremendous amount. And this chart primarily covers just what STMD is doing, but obviously SMD is funding a significant number of instruments that are applicable for resource assessment as well as the CLIPS missions. So there are several activities going on with respect to how you would acquire samples, understanding the physical and geotechnical characteristics of the regolith, especially in permanently shadowed craters, mineral instruments, in particular volatile characterization instruments, those that can heat up the regolith and actually drive off the volatiles and understand them, similar to what the SAM instrument is doing on Mars, for example. And then mobility aspects. How do we get our instruments into the different areas, the permanently shadowed craters? There's a number of different activities going on there. And if you look at the right-hand side, yes, if there is an X next to the electrodynamic dust shield on the Firefly mission in 2023, for example. So all of these things, even if they're not flying necessarily for a resource assessment mission, are demonstrating the instruments that could then be used later on. Next chart. From an ice mining perspective, we are looking at where the ice might be and how that might influence our mining operations. So what you see a chart is just one possible location we looked at. It's near the connecting ridge near Shackleton Crater. And so we wanted to understand if you put in a mining site there, what kind of traverse paths and you know, how would you set up your power systems might be. I'm not saying that that is the location, but it gives us an indication. So we have just three different mining techniques, just the excavation and delivery to a centralized processor. We look at subsurface heating in a contained device such as PVEX that Honeybees worked on, or others have looked at how you might heat the subsurface and have the volatiles come out and be collected in some kind of a dome. And so there are several different activities going on in each one of those areas. Next. For oxygen extraction from regolith, Dr. Larry Taylor's name came up earlier. He wrote a paper a number of years ago that I've continued to use this day that talks about lots of different oxygen extraction from regolith techniques. We've tried to work on several of those over the years. Carbothermal reduction of with methane is one. Molten regolith electrolysis is another. Those two have probably the most work. But there's some other interesting work. Ionic liquid reduction. It's a kind of a uh, acid type reduction. Using plasma hydrogen instead of just hydrogen reduction. And then there's always been the vapor pyrolysis aspects. The interesting thing is that we are now focusing on Highland materials versus Mare, which is what we looked at during the Constellation program, and we're seeing some significant differences in the processing techniques. Next. Um, the last thing I want to, I think, mention here is the water processing. So whether it's mining water or some of the oxygen extraction techniques make water as an intermediate product, we need to have water electrolysis and cleaning techniques and capture techniques. We are funding, along with our life support and regenerative power folks, several different technologies in the three main branches of water electrolysis: proton exchange membrane, solid oxide, and alkaline. Alkaline is interesting because it might allow us to actually have dirty water versus having to clean out the water as much. Next. From a very top level, our plan is from left to right, going from ground development, working on facilities and simulants. So, for example, the Johnson Space Center has a 15-foot diameter chamber that's being converted into use for regolith dirty testing. Um, there is a simulant project within NASA to help people understand what simulants they need for testing, as well as potentially production and distribution. Viper was mentioned. Prime 1 is a precursor to Viper. We're looking at 2 to 3 oxygen demonstration or ISRU demonstrations that hopefully will lead to a pilot plant by the end of the decade. Next chart. Um, from a lot of this is going on now. It's been mentioned, shadow cam on the Korean Pathfinder orbiter, Lunar Trailblazer, and the Artemis CubeSats are all going to help us better understand what's in the permanently shadowed crater. But LRO is that mission that keeps on giving. From a surface perspective, Prime 1 and Viper, Viper was mentioned, and Tony Colaprete will go into great details about that, hopefully. Um, as a precursor to Viper, we're flying the drill and the mass spectrometer on a mission called Prime 1 to buy down that risk even further. Somebody has an open mic still. Next, please. And then I think I'm going to end with just an idea to give you as to where we're heading. So when you look at the long-term commercialization, you're talking hundreds to thousands of metric tons of product. We had a meeting with the Lunar Surface Innovation Consortium, which basically said an initial mission might need something on the order of 10 to 30 metric tons. And so the work that we're doing now is to buy down the risk of that kind of plant. Initially in the tens of kilograms, the pilot plant hopefully will be about a metric ton per year, plus or minus some percentage of operations. And with that, I think I'm done. Next, takeaways. Hey, there are significant challenges and gaps that we need to overcome still. Resource assessment instruments are being developed and missions are being flown, but we definitely need more, as has been pointed out. We are developing critical technologies for oxygen extraction and polar water mining, and we are working with our materials, structures, and construction folks. And with that, I'll bring it to a close. Thank you very much.
Thank you very much, Jerry.